Environmental Industrial Hygiene Program. The core program is obviously industrial hygiene, but we do have a couple of alternatives. One is our Occupational Safety and Ergonomics program, which has additional ergonomics and safety classes that provides additional training, so you can have occupational safety and ergonomics background. And then we have a certificate program, biomonitoring, that allows you to also become an expert in the area of biomonitoring. Our program is really rooted in the core disciplines that we're trying to anticipate, recognize, evaluate, and control workplace environment exposures. We are very much about quantifying, objectively measuring the exposures, many different types of exposures, from chemical to biological aerosols to ergonomics and biomechanics, to lead exposure, environmental interventions, neurotoxic chemicals. There are many different aspects that we look at how the workplace interacts with the human worker, and both short-term and long-term ramifications, health exposures that's included in that. Our core faculty include myself as the director, Dr. June Wang as the deputy director, and then we have a very seasoned group of faculty members that is led by Dr. Bhattacharya in occupational ergonomics, Sergey Greenspin in aerosols, in bioaerosols, Lynn Haber in risk assessment, John Reichart in biomonitoring and risk assessment, and Tina Ruponen in bioaerosols and aerosols. So some of the highlights of our program: we're ABET accredited. Our master's degree takes about 2 years. Sometimes it goes over into the summer. The PhD is usually taken qualifier in the second year and takes about 4 to 5 years to complete. And our graduates leave with jobs. So this is the first year that I did not have 100% placement before graduation in the last 4 years. And I can say that the person that didn't get a job before graduation took 1 month extra, even in the times of COVID, and the shutdown of the economy. We're still seeing our graduates being placed rather quickly. And these are in jobs that are extremely high impact, whether it's a government, NIOSH, EPA, OSHA, FEMA, or academic with the PhDs at the universities across the world, or oftentimes private with large and small corporations or consulting. We have also multiple student organizations, a student chapter of EIH and AAAR chapters.
Hi, Dr. Grinchpin. Thank you for joining us today. So the Center for Health-Related Aerosol Studies that you have directed since the year 2000 is engaged in a variety of research, as well as the measurement and characterization of aerosol particles and the control of different aerosol exposures. The latter includes studies on respiratory protection. Can you please describe the main areas of your interests in the respiratory protection field?
Thanks for your question. So there's several of these areas. So the first one I would call would be new filtering materials. There are tremendous opportunities that we have now for synthesizing structures with special properties. One example to mention is nanotechnology that allows us to do that. So the filtering materials, including those developed for respirators, they may become much more efficient now due to this synthesis. So we are involved in the development of these materials and their evaluation as filters as well as part of respiratory protective device. The other area is a respirator fit. It is known that the filter may be pretty good in terms of efficiency of capturing particles, but the air may go not through the filter, but through the phase seal leakage. And in fact, under certain condition, when the filter material is very good, very efficient, the particles will go with this air following the path of the least resistance. And then the lion's share of the particles finally inhaled by the respirator wearer will be particles which penetrated through the phase seal leakage. So we are working on the new concept, the development and evaluation of new concept to allow basically zero particles penetrating through the leakage, or maybe very few particles, which in turn increases substantially the protection factor offered by this device. And then the final area that I consider very important is the respirator fit testing instruments, which are used for respirator fit testing of workers. There was one instrument which is called PortaCount, which has been around for decades. So we're working with companies to help them develop new alternative methods for fit testing, which hopefully will then be marketed and used in the field.
Great, thank you. So since the COVID-19 pandemic started, your respiratory protection research has been in quite some demand. What are the most significant and relevant issues in the mitigation of exposure to this coronavirus via respiratory protection?
Well, of course, the COVID-19 pandemic presented very new challenges in different areas, including the respiratory protection area. I will mention just a couple. The one is the fact that disposable masks and filtering face respirators started being used several times. So disposable is disposable. And before the pandemic, CDC was very clear on that, discouraging the repeated using or reuse of the respirators. I mean, filtering face piece respirators in particular. Now, due to a shortage of these respiratory protective devices, CDC actually came up with the new guidelines which allowed using respirators for several times, reusing respirators, and decontaminating respirators between reuse. So the crucial question here is not whether we can or cannot do it. Yes, now it's in the wide practice that people are doing that, and not really the question of the efficiency of decontamination methods. This area is quite well researched. But the question is whether or not a respiratory protective device will maintain the same performance characteristics, such as collection efficiency and breathability, after the decontamination, especially after repeated decontamination. So we have done some research in this area addressing specific models of respirator and specific decontamination techniques. Our paper that was accepted in August was just published in a major journal in the area, Clinical Infectious Diseases, and we hope to continue working on that. So that's about disposable mask and respirator during COVID. And the second area is the use of respirator by much greater number of people than it was the case before. Now, the general population is the main user of respiratory protective devices, not just workers. So we are talking about tens and probably hundreds of million wearers, and certainly hundreds of millions or billions worldwide, instead of several millions of workers who routinely wear respirators. And it presents multiple challenges. For example, the fit testing may not be done or practically cost prohibitive for the general population. General population is not as well trained how to wear respirators as workers, and several others. So we have been involved in the development of respirators that may be used by general population and we also designed a facility to evaluate these respirators on breathing mannequins and on human subjects.
Great. Well, thank you. And lastly, what are the future topics of your research in the personal protective equipment arena?
I think the future areas is continue, in my view, that continue being related to the development of new materials and the development of new approaches to face seal leakage, particularly for filtering face piece respirators. Again, now the combination of the new material and new approaches to the face seal leakage may actually be a very fruitful area for research, and we're going to participate in this research. And if reuse and decontamination continues being a hot area, in other words, if the respirators, the number of respirators available will not go up considerably. So this area has not been researched very well, and that's something that we're continuing doing. The last but not least, the masks and respirators, which are much smaller than those commercially available. I'm referring to children who now are required or asked to wear respirators and masks. And again, there are certain challenges related to small faces, to specific dimensions, spatial dimensions that needs to be researched.
Well, thank you. And thank you very much for doing the interview. I look forward to hearing more information as well as seeing some of the respiratory protection instrumentation in your laboratory. And I look forward to it. Thank you.
Thank you for your questions. Stay healthy and safe.
You as well. Thanks.
Okay, let me show a few things that we are using in our research on respiratory protection laboratory. So you could see here two mannequins with N95 respirators done on these mannequins. This part of the study relates to the particle collection efficiency that we measure by measuring the aerosol concentration inside this respirator and outside this respirator. These mannequins are connected with the breathing simulator, and we can always set and control the breathing flow rate, as well as we can set the pattern, the breathing pattern, which is individual for individual respirator users. Now, as we measure the concentration upstream and downstream, and then the ratio would give us the collection efficiency, we plot this concentration and calculated collection efficiency against the particle size. So you could see that the collection efficiency as a function of particle size is different for different masks and respirators. On the top, you see almost 100% efficiency or almost 90% efficiency for these respirators. And these are surgical masks, actually, with efficiency much lower than respirators. These are real data. You could also see that these curves are non-monotonic. They're very small particles, which are collected reasonably well due to diffusion. They're very large particles, which are collected probably reasonably well. But then those in between are not very well collected. And we continue investigating these curves in order to suggest some new filtering materials and new respirators that would have as high collection efficiency as possible. Now, sometimes if we investigate very high collection efficiency, we need to boost the concentration to have a representative number of particles inside the respirator. And for that, we use different aerosol generators. So this one, just to show, is generator that aerosolize sodium chloride particles. They quickly lose the water content in this chamber, and then they follow a specific particle size distribution, which is well characterized. So those research efforts are, as I said, devoted to the efficiency of respirators with the focus to respirator filter. But the collection efficiency is not the only thing. You have to use the respirator with a certain level of comfort. You should breathe through this respirator relatively easy, which comes to a criteria or to characteristic which is called breathability. The breathability is measured or quantified through the pressure drop through the filter. So we use this manometer to measure the pressure drop through the filter, and as you know, if the filter is very thick, it's sometimes difficult to breathe through this filter. So it may offer a good collection efficiency, but at the same time, in terms of breathability, it may be not as good. So we're looking at this characteristic as well. And then last but not least, if you happen to have a very good filter, what is important is the peripheral area, which may have a leakage. And then all your efforts that you spend to increase the collection efficiency, or almost all the efforts, will be wasted because the particles will follow the path of least resistance, and finally a lot of particles may penetrate through this peripheral area. So there is a test that measures how well this respirator fits the user. And for a long time, this apparatus, which is manufactured by TSI and is called port count, this apparatus has been around to measure the particle concentration inside and outside in dynamics and producing the ratio of this concentration, which is called the fit factor. This fit factor takes into account not only penetration through the filter, but also penetration through this peripheral area. And if you have a very open peripheral area, in this case your fit factor may go down and may fall below the certain benchmark, which is established for each types of respirator. And then if it happened in the field, you will basically tell your worker that he or she should reconsider and wear a different respirator model or different respirator size. Now, as I said, this port count has been around and we use it extensively. Like it also has been extensively used in the field. But it's relatively expensive and has some other issues. So there are a number of companies which attempted to develop some new fit testing instruments that could be cheaper, probably user-friendly, and they contact us and they ask us to help them develop, and what is more importantly for them sometimes, to evaluate these instruments against something which has been considered by some as a gold standard, which is this port count. So just to give you an example, that's the instrument manufactured by Shibata company in Japan, which has actually been introduced to the market last year. There are several other companies that are working on the development of these fit testing instruments that we are collaborating with. And we are using these mannequin studies as well as the studies with human subjects to evaluate these very important instruments which are developed to be used in the field in workplace environments to determine the fit of certain respirators used by the workers.
Hey everybody, my name is Vishal Nathu and I am a third year. I'm also a PhD candidate here at UC College of Medicine. I have with me today Dr. Jenny Cox, who is a postdoctoral research fellow under Dr. Raponen. Actually, we're both under Dr. Raponen, and we're both within the Department of Environmental and Public Health Sciences here at the University of Cincinnati. Dr. Cox has earned her bachelor's in biology from Wittenberg University, and then also her master's in environmental science from the University of Cincinnati. Dr. Cox worked for the U.S. Army Public Health Command before returning to school for her doctorate, which is a PhD in industrial hygiene in in 2018 here at UC. So I've prepared 3 questions for her, and those 3 questions are: what is the microbiome? Is there a healthy microbiome? And how do you analyze the microbiome? And Dr. Cox, would you care to enlighten us?
Sure. So first off, I just want to apologize. It says Charlie Cox down there, but I'm really, I'm really Jenny Cox. So I'm going to try and share my screen with you if I can steal the properties away from you.
Figure that out.
It disabled the screen sharing, so.
Allow participants to screen share. How about that?
There we go.
Cool.
That'll work. All right. So today, so what is the microbiome? Can you see my slide up?
Hold up, Dr. Cox. I can't see your slide.
Okay.
Perhaps you have, there you go. Now you have
There we
started
go.
sharing, but also,
So many buttons to click.
there you go. Now it's on. You're on. There you go.
That sounds good. All right, so what is the microbiome? The microbiome is anything that's microbiology in a certain environment. So it could be bacteria, it could be fungus, it could be virus. But so if it's in a person, then it's in, it's a human microbiome. If it's on your skin, if it's in your nose, if it's in your gut, that's all human microbiome. There's also environmental microbiomes where you're looking at dust, or there's plant microbiomes. I mean, it all sorts of different, you can imagine anywhere you can grow microorganisms, there's going to be interactions of all those organisms. So this is a good example of all the different bacteria species that is a part of your bacterial microbiome. So this doesn't even include the fungus. And you can see that a lot of actinobacters like your head, a lot of the proteobacters like different parts of you. So when all of these organisms kind of work together, we want to know like which ones are good or which ones are bad. In a healthy person, you can say that there's like, the overall goal of us is to figure out what microorganisms we want and which microorganisms are bad. But usually it's a delicate balance between the two. You can't really, it's not as easy as saying this one's some obviously are bad, but usually it's a nice dance between the two of them. So like if there's good digestion, then those are usually attributed to having good microbiomes. A lot of times if you have an infection or inflammation, those species would be like labeled bad theoretically. But really, like I was saying, it's a combination of your environment and your diet and your lifestyle. The first time you get your microbiome is when you first are born, very first day, day one. It's between the birth canal and your mother's milk, that's whose microbiome you get. You get your mother's. And ever since then, as you grow up, depending on what you eat, what you interact with, where you live, what kind of organisms are nearby is what's going to affect you and affect you and infect you. So the microbiome, like I mentioned, it can be on anything. So there's microbiome on plants where there's soil and on the leaves. And so if you have certain species of plants or animals near you, then those are going to affect your microbiome as well. So I lay all this out for you just to kind of give you an understanding that there's this is just an example of an interaction of how a fungus can deal with all the different bacteria that are out there. Like sometimes it's good and beneficial for the fungus, and sometimes it's bad, and they actually end up killing each other. So all the organisms are working together, and they're working inside you. I mean, there's trillions of them in your small and large intestine. So, the research that we do, that's all just like background. For all the research that we do to look at the microbiome, we look at the DNA-based approaches. So the DNA-based approaches are just looking at specific DNA sequences, and you're saying, okay, these are the bacteria sequences, which is the 16S, or the fungus sequences, which is the 18S or ITS region. There's a whole other different kinds of ways you can look at the microbiome, the RNA-based, the protein, the metabolite-based. But in our lab, we're focusing on the DNA right now. So what we do is we get a sample. We've done saliva, sputum, and dust so far, and we get a sample of whatever it is. We purify the DNA, we extract the DNA from the source. Then it comes into these little, we break it down into these little bar strips or gene codes, send it to the lab, and the lab processes it and identifies it as, gives us the genetic code And then we put that genetic code into a nice R package where we figure out what kind of phylogenetic tree it is, who the nearest neighbors are, who the, what kind of species it is, and where it belongs. So once we get the genetic code from the laboratory, we process the data through R, and then, so this next example is from a cohort of mine. She just graduated with her PhD in the spring. She did a respiratory microbiome, so she was the one who did the sputum and saliva. She, her name is Dr. Christine Nubel now. She looked at traffic exposure and how it affects your microbiome of your respiratory tract, and then also looked at to see if that was an indicator for asthma as well. So not that I'm not aware of her papers being published yet, so these, we don't have conclusive results or figures I can show you that are official, but basically she looked at the diversity of the microbiome in the respiratory tract to help to see if it increased asthma to diversity or decreased diversity, or overall increased overall bacterial load with TRAP is the traffic exposure, or with asthma status. So I believe she's still trying to work on getting those papers published currently. And then for my project, which I'm also still trying to get published, or I'm writing the papers as I keep working. I did the environmental environmental microbiome, there we go. So we have dust collected from carpet, and then we took that dust sample and analyzed it for the bacteria and fungus microbiome. We also had measured moisture damage and mold damage, and we had the health data from those children when we collected that dust sample as well. So the first thing we did was compare the mold or moisture damage with the different species. So this is just a brief glimpse of the species that came up with, if you have high moisture damage or high mold damage, these are the bacteria and fungus species that were more likely associated with those increases and decreases. And then we also looked at asthma species, which species are more likely associated with having asthma or not having asthma. So both of those different projects are looking at the mold and moisture damage. That paper should hopefully be out soon. It's done and being circulated amongst co-authors. And then the environmental one with the health data, we're actually just still trying to figure out what the best way to analyze the data is. So, but that's all I have as far as microbiome today. It was good talking to you. Do you have anything else, or?
Sure. So let me ask you some totally unscripted questions. How about that?
That's all right.
So you got your PhD in industrial hygiene, and now you are focusing on, I apologize, I just received an accidental FaceTime. Now you're focusing on environmental microbiome. So although some would say that is true industrial hygiene, some would say okay, that's not maybe practical industrial hygiene. So what made you get into the microbiome? What motivated you? So
the funny thing is so when I decided to go back for my PhD, I wanted, I knew kind of what area I wanted to work with, and I knew I kind of wanted to work with mold and fungus and indoor air quality, and Dr. Reponen was the one who did that. So, so that's why I ended up getting a PhD in industrial hygiene, even though it's not a traditional, I mean, it is definitely industrial hygiene, but it's not, I don't know, it's not ergonomics or,
industrial hygiene. Right. Very interesting.
Right. So I think I looked at biology, environmental engineering, all the different programs out there, and I knew that I'd wanted to work with Dr. Reponen before I even started. So
very nice.
Yep.
I agree. Dr. Reponen is amazing. She's really, really good to work under, and you learn truly a lot. Every day it's a new learning curve for me, and that's what the best part about it is.
Yep.
So thank you so much for your time, Dr. Cox, and for our viewers. If you guys have any questions,
Yep.
You have Dr. Cox's
Go
contact
ahead.
information.
Yeah, it's my maiden name in my email, so sorry about that. It's ROEJD. So.
No worries.
Yep.
If you have any questions for me, my email handle is nathuvd. It's spelled N as in Nancy, A as in Apple, T as in Tom, H as in house, and U as in umbrella. So at ucmail.uc.edu. Thank you again for everyone's time, and we look forward to any questions that you may have. Hey everybody, my name is Vishal, and I'm a PhD candidate here at UC. And today we're going to be talking about our environmental and industrial hygiene laboratory. So as many of you guys know, industrial hygiene is both an art and a science. As a true industrial hygienist, you need to be able to comprehend and understand the science behind what we do. And then to back that science and to practice industrial hygiene, you need to master the art. So this is where we master the art and also learn the science of industrial hygiene. So welcome to our lab. Typically, students who are in our first and our second years, whether you're on the doctorate level or the master's track, you do come in here and you sharpen your skills, and you're also introduced briefly to industrial hygiene concepts such as personal air sampling, air monitoring, as well as other numerous industrial hygiene concepts. If you walk around, you can see that we have numerous state-of-the-art equipment as well as legacy equipment, which is very important so students are able to understand how the evolution of instruments and equipment has evolved around the years. You can see that our boards here, our students have just completed a microscopic counting lab where they've counted asbestos fibers using various industrial hygiene techniques and media. Here we have numerous low-flow air sampling monitors for passive and active sampling. We have both active and passive media. We have brand new pumps as well, such as the SKC airflow pumps. And some of our legacy items, as Rashmi will show you, we have SKC chargers, things again to show the students how far we've come along with our technology. We have various media for analyzing, sending to labs such as particulates, fumes, vapors, things of that nature. We have various calibration media to make sure that all of our instruments are always calibrated before we place them on a student or on a worker in the field. A lot of interesting things that happen in this lab are primarily focused on industrial hygiene, but we also focus on occupational health and safety at large. For instance, when you're using some of our equipment, what are some of the safety things you should be worried about? For instance, what kind of PPE should you be wearing if you're breaking a solid sorbent tube to sample that way? All of these concepts are discussed in details in our laboratory methods. Some of our labs here on campus that we do include heat stress, ventilation, air monitoring. We do radiation detection, where students are actually training by a professional radiation safety officer here on site. So if you come on this side of the lab, you can see that we have different microscopes. We have different apparatus for analyzing samples. We have different cabinets, all labeled. For instance, this cabinet has impingers, which we can fill the impinger, connect it to a personal air sampler, fill it up with liquid, and then pour that liquid back into a vial after sample for analysis. Other items that we have here on campus include respiratory health. So as you know, I'm in Dr. Raponen's lab, and she is a bioaerosols researcher. Upstairs, there's a lab called the Centers for Health-Related Aerosols. In that lab, you'll find respirator mannequins where we actually test and study the dynamics of air and how PPE helps the worker or a customer. What my expertise is in biological aerosols. Some of the instruments that I use are brand new, novel industrial hygiene instruments, and the cool part about them is they are direct reading instruments. So with these instruments, I can direct read in real time without the need for laboratory analysis, and I can count how many biological particles there are, and I can differentiate between what's biological and what's non-biological. Some more items that we have here in the lab again. We have lots of respiratory protection because we like to study, what type of PPE is the best and what's the efficiency of the PPE. And again, we're able to teach all of our students the different types of PPE that's available to the workers. This section right here is where we do one of our labs known as the ventilation lab, where we study ventilation dynamics. We're using different types of industrial hygiene media to determine how many air changes an hour are in the laboratory. And we're actually forcing dry ice to overcome this room we leave and then we determine how many air changes an hour have gone through this room by using simple industrial hygiene techniques. Other than that, upstairs and downstairs we're also covered with laboratories. This laboratory mostly focuses on physical and chemical hazards. There are actually ergonomics laboratories on site as well that Dr. Davis and Dr. Bhattacharya do. So if you guys have any more questions, please feel free to reach out to us. Thank you.
Welcome to the Virtual Lab Tour. My name is Jun Wang. I'm a new faculty here in the Division of Environmental and Industrial Hygiene, Department of Environmental and Public Health Sciences at the University of Cincinnati. I joined the faculty here in the beginning of 2020, and today I'll show you the lab space and the equipment we have and several ongoing studies, and they will be shown by respective PhD students. We have 2 PhD students and we have 2 master students, all working on various projects related to aerosol and gases, emissions and exposures and their controls in the workplaces. Workplace aerosol and gas lab, also known as one lab, has various rooms spread out on the 3rd floor of catering lab. Room 354 is the main lab space. Here is second-year PhD student Thomas Girding.
Hi, so my name's Thomas, and I'll be showing you part of Dr. Wong's laboratory setup today. Over here we have materials which will be going towards our home stress study. We'll be starting soon. Basically, what we're going to be doing is sending these 50 milliliter tubes out to study participants, and over a few day period, they'll be giving us saliva samples. When they return back to the lab, we're going to measure the cortisol levels within the saliva to determine what the stress levels are that the people are working from home are currently experiencing because of the pandemic. We'll be using this immunoassay kit in order to find out what those cortisol levels are within the samples. So there's different solutions and supplies here for that. Over here, we have different power tool setups, as well as an air compressor and a shop vac and different supplies like that, because we'll actually be able to essentially manufacture parts of studies that we'll be performing over the next few years. For example, my dissertation topic is related to occupational exposures regarding electronic cigarettes as well as hookahs. So for part of one of my studies, we're going to try to create a smoke machine which will essentially show what someone may be exposed to while using a hookah or an e-cigarette in a laboratory simulation.
Room 325 is another lab space in one lab, and this is second-year PhD student John Singletary.
Hello, my name is John Singletary. I'm going to talk to you a little bit about what we're working on right now. I've been working with the Cincinnati Symphony Orchestra, and we've been doing aerosol sampling with them to help determine safe practices for social distancing in terms of COVID-19. So what we're using here is the PDRAC particle count, condensation particle counter. What it does is it enlarges the particles so it can be counted, and it enlarges it by aerosolizing, coating each one in 99.5% isopropyl alcohol. Inside this cartridge here is a wick that is saturated in the alcohol. We turn it on, we allow it to warm up. It warms up for 5 minutes, and then I can start programming it. And it's going to give us a count of the particles in the air. And so what we expect to see, the further away you get from a source of aerosol generation, is a significant decrease the further away you get. If you're not seeing that, then you need to reevaluate either your methods to validate your results and go back over it and make sure you're getting an accurate result, or it means that that distancing is inappropriate for that source of aerosol generation.
So in this lab space, we also host a couple 3D printers as our fabrication equipment. This is a Delta 3D printer that can print large-scale objects This is a laser cutter that's using carbon dioxide laser to cut materials such as wood, paper, cardboard. And then here is a dual nozzle 3D printer which can print two materials at the same time. And here are some SLA printer that's very different from the traditional concept of thermoplastic materials. Those 3D printers are used for two purposes. One, we are going to examine their potential emissions of aerosols and gases. Second purpose is to using them as a tool to develop innovative materials for industrial hygiene, such as copper-infused 3D printed face shield or other materials. Room 314 is a multi-chamber room that we use to do chamber studies. It can get pretty noisy here, so bear with me. There are 4 stainless steel chambers here that we can put various industrial equipment in that to study their emissions in a semi or fully enclosed environment. For example, we can do welding, cutting, 3D printing, or even granite cutting, all the fabrication, manufacturing, and the construction process. We can simulate them here. Those all the exhaust gas, we can capture them as a sample, or they will be directly outside the building. Those are stainless steel materials that's resistant to corrosions and all the other, they have superior properties compared to the traditional glass chamber. We also have a dedicated graduate student research office that graduate students can take breaks as well as working on literature reviews and other assignments. First year PhD student John Singletary is working on his thing, and along the bench, Tom Skirting is also working on his assignments. We have spots opening for other students, but due to the pandemic, there's various restraints for students actually coming here. But we also have amenities such as microwave and the coffee maker and the fridge for students to take a lunch break or something.
Hi everyone, my name is Rachel Zeiler and I'm a PhD student in the Industrial Hygiene program here at the University of Cincinnati. For this presentation, I'm going to talk about the Early Detection of Degenerative Disorders and Innovative Solutions Laboratory, or the EDDI Lab, that's been led by Dr. Amit Bhattacharya for the past 40 years. So just as an outline for this presentation, I'm going to go over the overall lab focus, the tests we use in the lab, some of our current studies that we're working on, and what we're planning for the future. As the name describes, the EDDI Lab focuses on the early detection of degenerative disorders by observing functional outcomes after exposure to physical and chemical risk factors. Most of the research done in the EDDI Lab has been on working populations, but some of our past and current studies have worked with children with early life heavy metal exposure and patients with degenerative disorders such as Parkinson's disease and osteoporosis. In doing this research, our goal has been to identify susceptible populations so preventative or control measures can be taken. With this, we hope to protect workers in susceptible populations, lower healthcare costs, and decrease disparities in healthcare delivery. The first test I'm going to talk about is bone shock absorption, or BSA. BSA is a non-invasive tool used to measure the energy absorption capability of the combined bone and musculature system. And I have a short video of how that test is done. So as you can see, during the BSA testing, the subject taps their heel on the force platform, and the sensors attached below and above the knee measure vibration energy transmitted through the leg. In 2004, BSA technology was used to observe preclinical signs of fractures in osteoporosis patients aged 65 to 85. As you can see on the graph on the left, osteoporosis patients with a history of fractures had significantly higher damping values at the below knee and upper back position. So this shows that those with a history of fractures had less damping capability of their combined bone and musculature system. BSA technology has also been used to study patients with early life lead exposure, and we hope to use it more in the future. We also use static sway testing to assess postural balance. A piezo-resistive force platform is used to measure ground reaction forces and moments. A custom software developed by our lab uses those forces and moments to calculate slight changes in movement of the center of pressure under the subject's feet during static tests. Our lab and others have shown evidence that exposure to neurotoxic chemicals and physical risk factors such as shift work and heat stress disrupts postural balance and increases the risk of falls. So we use sway testing to measure postural instability during static tasks. During static testing, we use a variety of different test conditions to challenge the three sensory afferents, which are vision, proprioception, and the vestibular system. For example, in the picture on the right, the test subject is standing on a 4-inch foam pad used to challenge the vestibular system and proprioception of the lower body. After our data is collected, we use another custom software developed.
Hello, my name is Kermit Davis, and I'm the director of the Low Back Biomechanics and Workplace Stress Laboratory. In our laboratory, we use very highly quantitative type of devices such as electromyography, the lumbar motion monitor that you see here. We quantify the stress on the low back during primary lifting conditions, but also looking at the mental sides of things. In recent years, we really have concentrated on healthcare. In this example, you can see how people in bed actually move down as the bed articulates. And we do a lot of quantification of how a person interacts with the bed, particularly when you are sitting upright. And as you can see, the problem here is that you have sliding on the bed as well as moving down and getting forces on the feet when it hits the foot section. The other aspect is that you can see in this case, a person here that's sitting, there's a passive migration. As you sit in bed, you shift down in bed due to gravity. We did a study basically observing 2 hours of people as they were sitting in bed. As I said, we have quantified various bed designs, looking at how they impact the way a person moves. The top left one is a complex pivot where you can see the patient does not move if you watch. And the other ones are actually moving closer to the foot of the bed. What you have to worry about is pressure ulcers as well as other and kind of nasty things that can go on. And then when a patient gets pushed all the way down, a caregiver has to move them up in bed, which causes a lot of stress on them. So our next studies that we've done is looking at various techniques to move a patient back up in bed. And what we have seen is that air mattress, this one down into the down to the left here, allows it to hover over the bed and allows them to move with various limited amount of stress that's being placed on them. All the other type of devices still remain pretty high on the stress levels. We also did a lot of maneuvering or looking at how patient beds are moved through hospitals, simulated in a laboratory where we're actually observing the stresses that are being placed on them using a power mechanism compared to pushing. And so the first condition that we looked at was just going straight forward and don't run into the wall. And as you see, they push it forward, they maintain a distance, and then they keep, without, and then return it. We also looked at going around the corner, which is also very interesting because as you see, you have to maneuver around various walls and not run into them, and use this with and without a power drive. And then the other ones that we looked at were up and down a ramp, which increases the load that that you have to withstand so you don't run into the wall outside the door. And similarly, going up the ramp where some of the caregivers weren't even able to push up into the ramp because of the amount of weight that was being placed on them. Another study that we looked at was with warehousing and looking at different interventions. One could be an intervention to the left here of a adjustable cart, which impacted the destination heights. We also then looked at a carousel and looked at how that raising it up and being able to turn it minimized the stress on individuals. Again, we looked at the spinal loads that were being placed on these individuals. And the real key here is that you have interventions that can affect the origin, which would be where the pallets are, and destination. And the real big bang for the buck was using the carousel. That's where we saw the biggest reductions. Another study we did was looking at the use of cues, where we had individuals lift the boxes as they came off a conveyor in front of them, and then they basically had ones that they were random and unknown. They had ones that were you could see the actual the cues here of high, low, medium weight boxes, and what we found was something very interesting, that with females, they would tend to drag the box to them, get a feedback, and then lift, where males would just pick it up and lift. And so they changed their kinematics with the way they moved in their lower back during these conditions. Our next studies we actually did in the field, where we're looking at a cart that was adjustable and compared it to their traditional flatbed study with the lumbar motion monitored. This was actually down in Puerto Rico, where we actually monitored people. These are actual workers in the workplace doing their task of stocking shelves in their little warehouse area of the grocery store. It was very interesting that we saw that you could reduce the sagittal flexion, but it actually increased the twisting because they were able to maneuver the cart much closer to them, and so they were twisting more. Another study was very interesting, was looking at Mason bags and looking at what traditionally is a 94-pound bag of cement or mortar, and we looked at reducing that to about a 47-pound bag. And what we found was, again, you actually didn't get cut the loads in half by lifting the lighter bags. We actually just looked at and saw that they changed their kinematics. They moved faster. They moved it away from their body more. So the peak loads were not exactly, you just didn't reduce it. It was about 25% reduction only. Again, we looked at spinal loads and lumbar motion, moderate motion. Another study we did was looking at sit-stand tables. We did it in a drug and poison information center. We looked at discomfort. So by introducing posture changes throughout the day, you can actually decrease the discomfort. You have no impact on the actual productivity of mouse clicks, typing, and actually saw increases in all of those, even though they were away from the desk more often. This was a study we conducted over about a 6-week or a 10-week period. Another study we also looked at was looking at mismatches of students and looking at how they fit their workstations. And what we found was every student mismatched one of the parameters, whether that's knee height relative to the seat pan, the interaction with the desk, in particular having issues with clearances. And we also found that there was a high level of discomfort, which is very disheartening for younger kids having significant amount of discomfort. And then the last study I'd like to talk about is a study that we looked at for shovels and wheelbarrow activities for children, where again we saw the benefits of different designs of the shovel, where the shovel on the right was an add-on handles, and then you can see in the left was the different types of wheelbarrows. There was 4 different wheelbarrow configurations. We were looking at dumping the material. We were looking at transporting it over both over a threshold and then just straight, and then shoveling out a stall with the actual ability to use the add-on handles. Again, it was perfect to have the add-on handles that reduce the sagittal flexion, how far they bent over. But again, it created a focal point where they did twisting a lot more. That's a summary of my laboratory, the low back biomechanics and workplace stress, where we do occupational ergonomics research. And if you need to contact me, you can contact me at kermit.davis@uc.edu.